Welcome. So this is 49A8 and this is about phase angles. What we're going to look at is oscillations that aren't well behaved. Let's look at this left-hand diagram to begin with. We move our block to the right and let it go exactly when time t equals 0. So this is very well behaved. And we can use our standard math and say the position at any given time is equal to a cosine omega t. It's just beautifully well behaved. All the equations that we've learned follow from this. But on the right hand side I'm showing a situation where something went wrong. We moved the block to the right hand side and we let it go, but we didn't start the clock at t equals 0. We started the clock a little bit later. And so what do we do about this? We still want the math to work. So what can we do? And what we realize is that all we have to do really is just measure, somehow account for this lag, this lag of the clock. It's still a cosine function. It still depends on omega t. It's just that when you should be at one point, you're delayed. You're somewhere else. But it's a constant offset error. I'm going to try and draw a curve in to show you. It's kind of like, yeah, we think it's doing this, but in fact it's always a little bit out. But it's a constant bit out. And so all I have to do is measure this time delay and express it in radians. Now, do I add that phase angle or do I subtract it? If the clock starts late, add the phase angle. If the clock starts early, subtract the phase angle. We're going to give the example in the equation of the clock starting late. So we started the oscillation, then we started the clock, you'd add the phase angle. It's a really kind of simple solution to what could be, on the face of it, a horrendous problem. Here's an example. So a spring and block system oscillates with simple harmonic motion. The block is displaced 3 meters to the right. So that distance there is 3 meters to the right of the equilibrium and released 2.5 seconds before the clock is started. Okay, so this will be one of those cases where we'd add the phase angle. The system has an angular frequency of this and it has a phase angle. And it says what is the phase angle associated with this motion. So what do we know? Well, we know that my amplitude is equal to 3 meters. And we know that our time interval, is equal to 2.5 seconds. And we know that our angular frequency is equal to 0.8 radians per second. And I want to somehow get an angle out of this. And again, that might not seem so comfortable. So I really am keen on using analogies. So yeah, amplitude is amplitude and delta t is delta t in the linear terms. But omega is like omega is like a velocity. It's an angular velocity. And we're trying to find an angle which is like a displacement or a position. I didn't actually write down my angle, so I want to find my theta, my phase angle. Well, we're calling it phi, my phase angle. Going back to this analogy, of course, then we could turn around and say, oh well, hold on, v is equal to the displacement over the time taken. So that means that the displacement is equal to v times the time taken. And by the same analogy over here, what I can say is that, oh yeah, this is going to be that my angular velocity is equal to my angle over the time taken. And so the angle is equal to the angular velocity times the time taken. And then I come along and here and say, well, my theta oh, I keep calling it theta, I'm sorry, it's phi. My phi is equal to my omega, which is 0.8, times my time taken, which is 2.5. So my phi is equal to 0.8 times 2.5. 0.8 times 2.5, which equals 2. So this will be 2 radians. Don't forget units, 2 radians. Now, if we say there's about 6 radians in there's 2 pi radians in a circle, which is about 6 radians in a circle. So there's about 6 radians in one circle, which is one cycle. And we're 2 radians along that. So it's about a third of a cycle, a third of a period. And if I look at this, then it's basically taking 1, 2, 3, 4 of those guys, 4 and a bit of those guys, and I'm getting basically, let's have a look. That's not quite a half. From there to there would be a half. So it's a bit, the angle is a bit less than a half of a cycle, more like a third of a cycle. So, makes sense. So again, can you see how it's actually mathematically very straightforward? It's just the terminology that we're very uncomfortable with. So the more you can live with this terminology, the better, the easier it gets. So there we have it.